Hi, welcome to the analysis and design of a flyback converter. This is part 20. Topic is transformer design. Actually, this is the third video on that subject. In the last video, we did a review of the design procedure, and we will continue to develop the design procedure with the end goal of perhaps putting this in a spreadsheet where you can then do actual designs at a very rapid pace. Okay, and actually do iterations interactively. In the last video, we selected, the core. We selected a EFD20 core, and that came from the AP calculations. Showed how to calculate the core losses using the plots. Also showed how to use the dowel plots, and also selected the wire based on the number of turns and the W sub W, which is the window width. And then verified if the wire can carry. Okay, so based on the last design example, we selected the wire, and based on the number of turns and knowing what the winding window is, or the width. In this case, the width is 1.35, and if we divide the window width by 17 turns, we get the diameter that we can fit 17 turns of wire. And we calculated that it would be 0.794 millimeters of width of the diameter. So in this case, we looked up this in a table, and the table says that we can use a 20 gauge wire, magnet wire, double insulated. Okay, so I want to preface this that this method of selecting the wire only works when you have a simple design. Simple design meaning one primary, one secondary. Now, if you have a big core, you might be able to fit that, but if you have small cores or you have multiple windings, you will not be able to find or fit the windings in your bobbins, because this method gives you a overestimate of the wire. It's too big. Okay, so there's a better way. I believe it's a better way of selecting the wire. Okay, and that is based on the size of the wire based on current. Okay, so let me go ahead and reiterate. This is the example that we're using, and I'm going to be using just the primary, because once you see the design method for the primary, then you can do it for the secondary. So in this case, it's 17 turns for the primary. Secondary is 9 turns for each, because they're 12 volts at 1 amp, 12 volts half an amp, 12 volts and half amp. So it's a total of 24 watts, basically, output. Okay, and by our analysis, we had calculated that the current going through the primary was approximately 2.7 amps RMS. Okay, so based on that, we can use a chart or table, or a table of wire versus current. Okay, so in this case, if we were to, let's say, use a table, okay, the closest 2.7 would be maybe a 24, 25, somewhere around there. Okay, or let's say if we wanted a 1 amp, then it would be a 30 gauge, so forth. Okay, so using the table, you use that, or the method that I would prefer to use is use the equations. Okay, and you can use these equations, which can be easily put into an Excel spreadsheet or MathCAD. Okay, and this is very powerful. If you can do it in Excel, then you can have a very interactive spreadsheet. Okay, so we started with this equation. Okay, this equation determines the current of the wire if you know the diameter. Okay, that's the diameter of the wire, and it calculates the current. Using that equation, if we solve for D, we end up with equation 1. Okay, so in this case, if we enter the current, in this case we would enter the current there, 2.718 or something like that, whatever the current was, and we end up with the diameter. Okay, so this can be easily put into an Excel. That would be equation 1. Okay, and the units are in meters. Once you have the diameter in meters, then you use equation number 2. Okay, you enter your diameter of the wire that you calculate for equation 1, and you end up with the gauge. Of the wire. Okay. I'm sorry, I misspoke. I said that it was 2.7. It's actually 2.17. Okay, got that mixed up. So where am I? Okay, here's the actual current. Okay, so this is the current of the primary. These are the secondaries. Okay, so this is the current that we are interested. Okay, and plug in this number into equation 1 first, and then into equation 2, when we end up with a gauge of 25. And if you plug in these other currents into 1 and 2, you end up with a wire size of 26, 30, and 30 for the secondary windings. Okay, so this is iterate. In other words, this is the first pass. You can go back and forth and change them. And typically, you can go up in value, bigger, make them bigger. But remember, you can't make them smaller unless you parallel wires. Okay. So once we have the gauge, okay, we have this information. We know that the primary, we're going to use a 25 gauge wire. So, and from the previous, we determined that we were going to use the EFD 20. Okay. So we need a fourth parameter off of the data sheet. And that parameter is this, MTL. MTL means mean turns length, meaning that if you have a core or a bobbin, and if you wind one turn around the bobbin, and then you measure the length of that, that means that one turn will give you 3.41 centimeters. That would be the length of this turn. So that's very advantageous, because if you know how many turns you're going to put, in this case we're going to have 10 turns, if we'll multiply the turns by the mean turns length, we end up with the length. In this case, to put in 11 turns, we're going to have 11 point, I'm sorry, we're going to have 0.3751. this is the turns. Sorry, 11 turns times the MTL. That is this, and that is that. So here's the answer. 0.3751 meters. Okay. Once we have the length, then it's pretty straightforward to calculate the DC resistance. Here's the DC resistance of the primary that we're evaluating. Here's rho, which is the resistivity of copper, which is 1.68 to the negative 8 meters per ohms. Okay. Divide that. Multiply times the length of the wire, which is where already calculated, divided by the area cross section of the wire. In this case, I like to use, instead of radius, I like to use diameter. Okay, so the area is pi diameter squared divided by 4, but the 4 comes up here. Okay, you end up with this equation. If you wish, since the length is, you could substitute that in there, turns times MTL. Okay, so you end up with equation number 4. Again, the diameter size, that comes from equation 1. That's the diameter that you the wire that you're using, or the current. You put it in there, and you end up with the DC. Okay, so when I plug in my numbers, I end up with the DC resistance of 29.3 milliohms. That's there. Okay, so let me go ahead and stop there, and if go to the spreadsheet, just in case. I want to give you a how it would look if you can input into a spreadsheet. Excuse me. Okay, so in this case, this is the current 2.173. Okay, and I use equation 1, and then equation 2, and in equation 2, after equation 2, it's supposed to give me the suggested gauge of the wire based on current. So in this case, it's telling me that it's 25.7. Okay. Now this is the suggestion. I can't move this or change this. This is an output. So everything in blue is output. Everything in yellow is an input. So in this column, this is for the primary. I have 3 variables that I can play with. I can play with the number of wires that I can use, and the number of layers, and the size of the wire. So those are the 3 parameters that I can change. Okay, so all the calculations are based on this. Okay, so here where it says wire size, I have a 28. Okay, 28 gauge wire, and suggesting 25. And if you notice here, it says current per wire 1.4. This 1.4 is lower than the 2.17, so it flags it as red. Okay, now if I put 2 wires of 28, then this should double. It should be 2.8. So let's do that. Change this to 2 wires, 2.8 or 2.9. Okay, so it's double the wire, and then it turns back to blue. Okay, so but let's go ahead and keep this to 1. Okay, and let's go ahead and use what the program is letting us know. Use 25, so we change it to 25. Okay, so now based on 25 and using the equation that I just stated, then I come over here where it says RDC. You can see that it says 29 milliohms. So by using the equations 1, 2, and 3, and so forth, I've calculated all these values, also the diameter and so forth. Okay, so let's go back here. So now we're ready. Now we're ready to calculate the AC resistance. The AC resistance, okay, there's two ways. And remember, the AC resistance are due to the skin effect and the proximity. T. Okay. And to calculate the AC resistance, you need to find the FR coefficients, and that is done from the Dow's plots. Okay, so you can do this graphically. That was done in video 19, the previous one. Okay, but I prefer to use this method. That is, use the equations from Dow's. Basically, use the Dow's equation, put them in MathKit or the Excel, and then use that as a interactive. Okay. So let's see. Let's take a look at the equations. There's two constants right here. That constant is used in this equation right here. This is skin depth. Okay. Here's the two constants, and if you notice this frequency, so that frequency is the frequency, and then my example I'm using 100 kilohertz, and that's the switching frequency. Switching frequency. Okay. And then you have your Dow equation here. Let's see, do I have an equation here? Let's say 5. I'll label this equation 5. Let's see. Yeah. Actually, we'll do this equation 5. And we'll make this equation 6. Or these main equations. Okay. Okay, so then the skin depth is calculated, and that is used within the Dow equation there. Let me make this a little bit bigger. It's used there, and so forth. Okay. But I want to point out this here. That's the skin depth. Okay. And X is the diameter of the wire. So it's a ratio. Okay. Ratio of the wire to the skin depth. Okay. And that is actually your independent variable. Also want to mention there's another independent variable, that's the layers. Okay. So that's this section here, these terms. Okay. And depending on the number of layers that you're going to be using, you get n type of coefficients. What do I mean by that? Let's see if I can explain that a little bit. Okay. The main goal is use one layer per winding, if possible. Why? It reduces these coefficients. In other words, if you have one layer, you can get all your windings in there, then you only need one coefficient, which is 2.48. But let's say you can't fit all the wire in one layer, and you start here, and then you start the second. That's another winding, and then you go back and do the third winding. So now you have one winding, one layer, 2 layers, 3 layers. So if you have 3 layers, then you need 3 coefficients. You need that one, and so forth. Okay. So if you have 3 layers, then the coefficient is that you're going to be using to multiply is going to be the average. So you would use 2.481 plus 7.607 plus 16.15 divided by 3. That number then is used to calculate your DC. Okay, so in my case, I'm just using 1 layer, so I only need 1 coefficient, and that's what this is. Okay, so the AC resistance is the coefficient, first layer, times, and here it is. It turns out to be 2.481 times the DC resistance of 29.3 milliohms. So basically it's telling me that it's almost two and a half times bigger. So you end up with 72.3 milliohms, almost 73 milliohms. Okay. Once you have that, now you're down here. This is what you really want. You want to calculate your power. Okay. So the power is the current squared times the DC resistance plus the RMS current squared times your AC resistance. You total that. You can factor out the currents, which I've done right here. Okay, so I end up with a power of 479 milliwatts. Okay, so this is the main goal. You want to calculate the power, and remind, this is just the wire losses. Okay, these are both conduction and both AC, DC, and AC. Okay, that's the total. Okay, so you use the same procedure basically to do the secondary windings, and you can put these equations, you can put them in MathCAD, or you can put them in a spreadsheet. Okay, so let's go ahead and minimize this, or put them all together. Okay, so here on the second, this column row, here's the DC resistance. Using the equation and using the Dowell equation, the Dowell equations are calculated here. Okay, here's my equations. Okay, and once I get that, I use them over here to calculate my AC resistance. So in this case, I calculated here approximately 73 milliohms. Got 73 milliohms here, and then I went ahead and calculated the power individually. The power dissipated by the DC resistance is here, 138 milliwatts. AC resistance 343. So you notice the AC resistance higher than the DC, and then you sum these two together and you end up with the total. So here's the power total, 482, 479. So pretty close. Okay, so now we've pretty much done. We have a spreadsheet that we can go ahead and use, optimize. Here's the spreadsheet. Okay, here's the number of turns, 11 turns for the primary, 5.5, 5.5, and so forth for the secondaries. Then I can go ahead and here I can enter my voltages and currents. 12 volts 1, 12 volts half an amp, 12 volts half an amp. Okay, here's my current, 2.178, 1.78, 0.89, 0.89. These are the same. Okay, so again, here's my suggested current, or a suggested size of wire that I can use. This one's saying 25, so I already done that, 25. So here I have 26. Okay, then I'll go ahead and use this as 26. This one is telling me go to 30, so I go to 30. Okay, Now mind you, if I use 31, which is a smaller diameter, it flags it. It says, hey, you're under the current. So you gotta use a bigger wire, so it turns off. And here, 30. Okay. So what I've done is, now it's already calculated the DC resistance on our 4 wires. It's calculated the resistance, AC resistance of all 4 conductors. And more importantly, it's calculated the current, or actually the power dissipated in each winding. So here I have 482, 184, 81 and 81. Okay. So I total all of that, and it comes out to 828 milliwatts of power. Okay. And we have 333 milliwatts of core losses. That's there. So if I add these two up, I end up with 1.16 watts of power. And I end up with an efficiency of 95.7. So let's go ahead and copy that. See if we can improve. This is first pass. And okay, I already have it here. Okay, so now this is where the power comes from. We can optimize it. We can do what if scenarios. Okay. So let's take another look at the spreadsheet. Okay, calculate the power. Now here I have two other values. Here's a percentage of the layer filled, okay, and percent of the height. So let me explain this one. This is telling me that if I use a 25 gauge wire using the bobbing that I'm using, and I put 11 turns, that it's going to be about 42, basically almost 43% filled. Okay, meaning that if I have my bobbin, I start with 1 turn, and then the 17 turns is here. So okay, so from start to here, that's almost 43%. Okay, so that means that this is empty space, mostly empty space. Okay, so that means that it's not completely filled, and you want to most of the time you want to completely filled if possible. Okay, if you can get above 90%, that'd be great. Okay, so now take a look at this. Okay, mind you, take a look at two things. I think I already showed that if I increase with 1 wire, I have 29 milliohms. If I put 2 wires, this went in half. In other words, it's 14. And if you notice, this used to be 480 milliwatts. Now it's 241 milliwatts. So the power dissipated and improved and went down. So now, look at that. It used to be half of this. Okay. So now I'm at 85.2. So I'm getting there. Okay. So let's go number 3. What would happen if I use the 3rd wire? Well, the wire reduces, the power level reduces, but now I'm at 127 filled, meaning that I can't squeeze them in. It's too many, it's too big. There's 2 options that I can do. I can use 3 and then use a smaller wire. I can use maybe a 26, let's see. Nope. Go 27. No. But a 28. Okay. I can use the 28 wire and I'll be 92% filled. That's great. Okay. Still have less than the 480. So that's an improvement. Okay. So this is 3 wires. So this is called trifilar. Okay. Now let's optimize this. Okay, I'm at 19%. Okay, so I can increase to 2. I'm at 30%. 3, 57%. 4, I'm 76%. Okay, so now 4, that's quite a bit of wires that you can wind. That's a quiet filer. Okay, if you go any higher, you can, but it gets a little bit more harder to do. So now I only have 76% filled. So what can you do? Well, you can make the wire bigger. Okay, and you make it by setting this at a lower number. So let's try at 25. Okay, 25 gives me 85% filled. Let's try at 24. Okay, now in the 90s. So I think I'm happy with that. 95 right there. Okay. Okay, so now here we have this other one winding, only 12%. Let's go again, set these 4, 50%. Okay, well, let's go 5. Maybe 5 is still doable. 60%. Okay, so now we can increase this. Let's say at 28. 28, it's at 76%. Let's go 2 numbers, go to 26. I'm at 95%. Okay, so now these two are the same, so I can use the same configuration. Go 26, make this 5. Okay, so now I come and check over here, copy this, let's do compare it. Okay, okay, so now this is the first pass. Or first iteration. Okay, so we ended up with 828 milliwatts of power loss in the wire, but after optimization, we ended up with 292 milliwatts of power. Okay, so we did good here. Look at the efficiency. We started with 95.17, and after we optimized it, raised it up to 97.4. Okay, which is good. So that's the power in having a spreadsheet where you can do that very fast, very interactive. Okay, so here's kind of like the flow. Okay, you start with your RMS. You enter into equation 1. You end up with the diameter of the wire. Once you have the diameter of the wire, you enter into equation number 2. So you get the suggested wire gauge. Okay, should not be smaller than this. Okay, that's important. Where are you? Right here. Not smaller. Not smaller. And then you decide what gauge you use. You enter into this equation again. That equation then calculates the wire that you will actually be using. So you're going to end up with the diameter. Then that diameter is entered into this equation to check the diameter that you're using, to check whether it can carry the current. At the same time, that same diameter is entered into this equation, which is used to check your DC resistance. Once you have your DC resistance, you can use the Dowell equations, okay, and you use it to calculate your AC resistance. Once your AC resistance is calculated, now you can calculate your total power, which is what you really want. You want to calculate the power because why? You want to evaluate your efficiency. Okay. Once you have the total power, you enter here. This is the output power divided by the output power times the total power wasted. Okay. And remember, this is 2. This is only half of the equation. This is power losses due to the wire, which is this. This power associated with the core, and that was in video 1. No, video 19. Okay. Once you have that, you can get an efficiency. So that gives you a way of checking and verifying whether your design is good or not, or whether you can improve on it. Anyway, this is a way of showing you how you can implement into a spreadsheet, which makes your design process a lot faster, more interactive, gives you more iterations to improve your transformer. I know it's a lot of material, a lot fast paced, I guess. And if you have any questions, maybe I didn't explain something as well, feel free to email me at my email address, or you can post your questions on my VideoTube or YouTube channel. I'll try to answer them as quickly as possible. But again, if you have questions or comments regarding the lecture, would appreciate the feedback. Okay, well, thank you for watching. Hope you have found this informative.